Okay, recording started. Very good. Now let me share the screen. Good. Now, okay. So this is my web page. Just 1 second. I want to open also the phone because I wanna check that you see what I suppose that you see. So I just need to check on the phone, even if let me deactivate the Wi-Fi because I don't want to. The connection is already weak today, and let me use another connection for the phone. Okay, good. So let me just check, restart from scratch because I wanna. Okay, good. Okay, now you should see the web page. So this is the web page of the course. Let me click again on beach hydrodynamics and morphodynamics, and let me go to the point where we got last time. But before moving forward, just let me go to the Csc formula. Yeah, here we are. Let me expand a little bit. So last time we introduced this formula, the CIRC or CERC formula, which assumes that the sediment, the longshore sediment transport is proportional to the flux of energy of the waves. This flux of energy is computed at the breaker line. Why at the breaker line? Because it is the time and the site, the location, where the energy of the waves is transformed in a movement of mass. And it is the place where energy gives rise, after breaking, to the movement of mass that erodes the sea bottom and transports the sediments. So under this assumption, we wanted to compute the flux of energy that is originated by the waves. Okay. Let me step back a little bit because I want to make sure that you understood what we did. And I think this is the right time to make this collective brainstorming. It is the right time because I think this concept is a concept that needs to be digested. And for this reason, I decided last time to introduce this energy computation and to give you 1 week before making this additional considerations. These additional considerations, again, have the purpose of checking in a way if you fully understood how the energy of the wave is computed. I think that probably you don't need it, but in any case, I think it is helpful because even if you fully understood what we did, I think it is helpful to try to better see at a technical level what we are really doing. So let me just make a simple example because if you look at this formula that you see here, and let me show you the formula in particular. If you look at this formula, it is a formula that computes what the potential energy of the wave, we said per unit horizontal area. And so this is a concept that it's not so easy to get. So I just wanted to now step back a little bit in order to better explain why we computed the potential energy in this way, why we took the average in the first addendum at the right-hand side in order to, as I said, better clarify. Okay, so let me refer to a simpler example, to a conceptual model, a conceptual situation which is much simpler, because here the situation is a bit complicated because we have a wave that is going up and down. We are computing this energy before the wave breaks. It's going up and down. So in a way, the geometry of the volume of which we want to compute the energy is not fixed. This is the reason why we decide to take the average. But in any case, let's refer to a situation that is easier. And before I start, let me just remind you that here we are computing the energy above with respect to a plane. We always compute the energy with respect to an horizontal plane. And here our horizontal plane is placed at the mean sea level. So again, the energy, the potential energy is always computed with respect to a reference horizontal plane. And here it's the mean sea level. Okay, now, as I said, let's refer to a simpler situation. And let me take a graphic window, and let's refer to a situation which is a fixed shape, a cubic shape. So let me see if I have, yes, I have already here the pen. So let me refer to a cubic shape, and let me just make it a bit longer here, and also here a bit longer. Okay. And let's take this cubic shape in 3 dimensions here, and then here, a little bit shorter here. Okay, good. Here, here, and here. Okay. Let's suppose that we want to compute the energy not of a wave with varying geometry, but the energy with respect to an horizontal plane, which is located at the base of this cubic shape. Okay, now let me just remove this line here. Good. And now let me draw with the red. Let's take the reference in this way. Good, and let me just take the black here. Okay, so let's take the references, the direction of the axis in this way. This is Z, this is Y, and this is X. And in particular, this X is the cross-shore direction, cross-shore. And this Y is the transversal direction. Transversal direction, okay. Okay, so again, let's compute the energy of this cubic shape, which we assume it's full of water, with respect to the plane Z equals 0, Z equals 0. Okay, and let me indicate with ZG the elevation of the center of gravity. This is the center of gravity. Okay, now, how do we compute the potential energy? The potential energy, let's call it simply EP now. It's given by the weight of the shape, and the weight of the shape, we can indicate it in this way. Gamma, specific weight, gamma of water, times the volume of the shape, times Z, Z, G. This is the potential energy, okay? Mass times the elevation of the center of gravity. Okay, now we can write it in this way. EP gamma is equal to the multiplication of the mass density times G. Again, times V times Z G. Now, let's suppose that the dimension of this cube is, let's say, 1.5 meters, 1.5 meters. And here the dimension is 1, the size 1. And let's also assume, let's also assume that the dimension here is 1 in the cross-shore direction is 1. Okay, so the volume, I can simply write the volume as the product of the three dimensions. EP, EP is equal to rho G. Instead of V, I put 1 times 1.5, and then again ZG. This should be elementary to understand. Now, let's say that, let's call it now, let's compute the energy per unit horizontal area. In this case, it doesn't change much because the horizontal area is the product of 1 times 1. You see, it's the product of the size in the transversal direction, which we indicated with Y, times the size in the cross-shore direction or longitudinal direction, which is again 1. So what we can write here is simply rho G 1.5 Z ZG. Again. Okay, and at this stage, given this very simple shape, our computation is finished. But now we have to refer to a wave. The wave does not have a fixed geometry. So the wave is something like, it may start from here and then, oops, I didn't change the color. I wanted the blue. So the wave starts from here and it may go down and then up again in this space, okay? And the same on the other side. So it may go down and then up again. So the geometry becomes varying, and this is a complication, of course. And what we need to do in this case is then to pass to an integration, because keep in mind that in this configuration, the blue line, the height that was fixed in the previous situation, 1.5 meters, now is varying. So if we want to compute then the energy, the same energy for unit square area, now I have the problem that both 1.5 and ZG are varying for each fluid particle that is contained into this geometric volume. And for this reason, I need to write, and let me use the blue, EBP is equal to the integral between, let's say, 0 and eta of, again, rho G, and let me call it now, because it's varying, Z in the Z. And you see something very similar to what we computed before. But again, this wave is going up and down during the phase, and therefore this eta is continuously varying. And when I move along the x direction, this eta again is continuously varying because it's a wave. And for this reason, I need to refer to an average situation. And I didn't have this necessity before because the cubic shape the center of gravity was already indicating an average situation for the cube. The center of gravity, being the center of gravity, is the average elevation of each fluid particle. In this case, eta is varying, and therefore I need to compute here the average over several values of eta, the average along a wave phase. Why along a wave phase? Because the wave phase generates all the possible values of eta, and this is why I needed to compute the average. But you see that the body of the equation is unchanged. And what does it give to you, this equation? It gives the potential energy now of the wave per unit horizontal area. Per unit horizontal area, why? Because in the computation of the volume, I'm only considering the height here, which means that I implicitly assume that the dimension of this volume, now given by the sea bottom and the wave crest, the dimension in the transversal direction and in the longitudinal cross-shore direction is 1 meter times 1 meter. And therefore, this gives an explanation of why this formula, which is very similar to what we computed in the web page, I go back just a little bit. You see, this is, if you look at the integral, and let's forget about the extreme of integration. It's minus dB here. I will discuss about this later. But if you forget about the lower extreme of integration, you see that the integral is precisely the same integral that I computed here. And this explains why this integral gives to you the energy per unit horizontal area, and also explains why I need to take the average. Now, this integral that you see written here, as I said, it's not the same integral that I wrote in the web page here. So let me explain why it's not the same, because in this simplified scheme, I wanted to compute the energy of the wave with respect to an arbitrary horizontal plane z equals 0. Now, if I want to compute from the sea bottom, what I should say, right, is here E B P is equal to the integral from minus dB to eta of, again, rho g z in the z, again, average. This is energy per unit horizontal area with respect to the sea bottom, but we said that we want to compute the energy with respect to the mean sea level, and this is why I have to put here an integral with the negative sign from minus dB to 0, because z equals 0 is the average sea level, of, again, rho g z in the z. And this is precisely the same equation that you can see. I move to the web page here. Precisely the same. So what is this? Again, it's the potential energy of the wave with respect to the average sea level. Only potential energy. And then we said we need to add the kinetic energy, which is the same. And this is why we end up with, I go back to the web page, we end up here with, just 1 second, we end up here with, let me increase the size again, with this expression, which is equal to the previous one, with the difference that you divide by 8 instead of 16. Let me go up. You see here you had 1 over 16. And here you have 1/8. Why? Because we wanted to double the energy. Why did we want to double the energy? Simply because we wanted to add the kinetic energy, which has the same amount on average along the wave phase, on average, of the potential energy. So let me go back to the graphic window. I hope that this explains better what we did. And in particular, I hope it explains better what we obtained. And I hope you understood why we obtained an energy per unit horizontal area, which is something that is, I believe, probably was not so clear before. Do you have any question on this? No questions. Okay. Now, let me just open another graphic window, just in case I need it. This is not a good thing because this is in red, but we can just, okay, do this. Give me 1 second. Okay, perfect. Good. Now, last time a bit forward, and we said that in order to compute the energy flux, because what we computed so far, it's again energy per unit horizontal area. In order to compute the energy flux through a vertical plane of unit width and perpendicular to the wave longitudinal direction, we need to multiply EB, which is again energy per unit horizontal area, times the group velocity. Perfect. The group velocity, we said that it can be estimated through this relationship that you can see here, which is basically, it's the group velocity is given by the product of G, gravity, dB. dB is sea depth, so it's the depth of the sea bottom with respect to the mean sea level, to the power of 0.5, so it's the square root. And in turn, dB can be expressed as the ratio between HB divided by K, where K is the breaker index. Okay, and HB is the wave amplitude, the wave height, sorry, the wave height. Okay, now, finally, we said that we define the potential, don't forget the word potential, the potential, a longshore sediment transport rate, PL. What is PL? It is the immersed weight of sediments per unit time that may be potentially transported. Okay, and we defined it in this way. So basically, PL is given by the energy flux, EBV, times sin alpha and cos alpha. Alpha B is the acute angle between the breaker line and the coastline. We already explained why we are multiplying times sin alpha to find the component, the longshore component of the energy. We also explained why we multiply by cos alpha in order to take into account that the braking action, the braking of the wave is in a way less energic, less impactful on erosion if the waves are approaching the coast in a direction that is closer to the longshore direction. we already made some reasoning on this, and so I assume that this reasoning is understood. Okay. Just take into account that the most impacting situation according to this formula is given by alpha. Here I forgot a b. Just 1 second, I take a note, because here I just put alpha. You see here, I should have put alpha b. So let me take a note. I'm correcting later on. Just 1 second, please. By the way, if you see errors in these pages, I would appreciate very much if you just let me know. If you let me know, because you know, these are evolving pages. I am making changes continuously in time, and I highly benefited from previous revisions by students. Okay, now we can transform this relationship here with simple trigonometric transformation in this one. So let's see once again what we have selected here. Okay, remember that CBG is the group velocity, EB is the energy flux. It can be written in this way, and it is a simple trigonometric transformation. And if you can check easily in Excel that it works. Now, it's important, the next step, which is purely empirical. Now, the actual, because before the now we talked about potential, immersed weight transport rate. Now we have to turn to the actual. The actual is the truth, is what really happens. Potential is what could happen. Actual is what really happens. And therefore, in order to get the actual, the truth, we multiply the potential, PL, transport rate, by an empirical coefficient K. The actual transport rate is reduced with respect to the potential transport rate, and therefore K is included in the range between 0 and 1. Very good. What is the ideal key value? We will discuss later, okay? Now, again, keep in mind that EL is what we were looking for, but it's the transport rate in terms of weight of sediment, precisely, immersed weight, okay? Now, if we wanna find the volume transport rate, QL, which is something that probably in technical application is more useful than the weight of the sediment, the volume is more useful, because usually you want to estimate how much a beach is eroded in terms of geometry, not in terms of weight. You are not interested in knowing that you are losing 10 kilograms of beach every day. You are interested in knowing that the coastline is moving back towards the land maybe 1 millimeters per day. And this is why very often you are more interested in what we call here QL. It's the volumetric transport rate. This formula is a simple transformation which takes into account the mass density of sediment grains, rho S, minus, because we were talking about immersed weight, so minus rho, which is the density of seawater. So when you subtract from rho S, you subtract rho, you obtain the immersed mass density. And of course, rho is lower than rho S, because otherwise sediments would float, given that sediments are heavier than water, even salt water. Salt water is heavier than fresh water. But in any case, salt water is definitely lower in terms of mass density with respect to the sediment. So this difference, rho S minus rho, is always positive. So if you take into account the weight and you take into account the porosity of the sediments, which is given by the volume of void divided by the total volume of the sediments, which means that n is in the range, is included in the range 0, 1, okay, where 0 means compact sediments. Of course, you will never get to 0, but close to 0, it means that the sediments are very compacted. If n approaches 1, it means that the volume of voids is closer to the total volume of the sediments, which means that you have the voids that are much more important in terms of volume than the sediments. So basically, it means that you have very coarse sediments with a lot of voids, but n is anyway always included in the range 0, 1. So this relationship, which takes into account, again, the mass density of the sediment, the mass density of the seawater, the gravity, and the porosity n. This is a simple relationship that allows you to pass from the transport rate in terms of weight to pass to the transport rate in terms of volume. Okay, and what about the K coefficient? You know, as I said, it's an empirical coefficient. We have values suggested by the literature. And how are these empirical values determined? Typically, you determine these empirical values by means of lab experiments or by means of in situ measurements. So let's suppose that you can measure the height of the wave. You can measure the behavior of the waves, because maybe you are observing, you have a monitoring system that allows you to get all the details about the waves. And let's suppose that you have also sediment traps that allow you to estimate the longshore sediment transport. Then you compare the estimated values of the sediments, of the sediment transport rate, the estimated value through the Csc formula, you compare them with the observed values. And then you get an indication about the value of K, because of course, if you see that the computed sediment rate that is given by this formula, let's suppose that you got a K equal to 0.7, as it is suggested by the literature, then you compute the sediment rate according to this formula, fine. Then you measure the sediment rate, the true sediment rate, and maybe that you realize that the true sediment rate is lower. Then it means that you have to change the value of K to match what? To match what you observed with what you simulated. Because this is a way to refine your model, to refine your empirical model. Again, this is an empirical model with a physical basis. The physical basis is clear because we started from the computation of energy, etc. But then we introduced an empirical coefficient. So it becomes a mixed model, empirical, physically based, and these models needs to be in a way refined through empirical, experimental observations. And this procedure of refining the parameter values of models by comparing what you observe with what you get from the model is called model optimization or model calibration, or you may say parameter estimation. The literature gives this value of 0.7. Of course, it is to be interpreted as a very rough indication, a very coarse indication, because it is computed by looking at what happens in several beaches, and then you get an average value. But of course, local conditions have an influence on the K value. And also, for the same place, the K value may change depending on the intensity of, on the behaviors of the waves. So you get a storm. If you get a storm, for instance, instead of a wave that is milder, then you may expect that K is increased. And also it may change in the season, according to the season, of course. Okay, now let's assume that we understood what we did. Let's see at what we got here. We got a relationship that gives us an estimation of sediment transport rate. This estimation is usually done at the very local level. So you cannot estimate the sediment transport rate for a beach that is, I don't know, like 100 kilometers long. It's too long, because here you refer to what? You refer to very specific situation. You refer to a wave height, you refer to a sea bottom depth, you refer to some porosity and mass density of the sediments. These behaviors change. If you move along the beach, these behaviors change. So if you move, like, for instance, think about the angle alpha b, which is the angle between, again, the wave direction and the coastline. This angle continuously changes, which means that you have to change the PL value in the formula that you see on the screen. And even if you move like 10 meters, the angle may change. And this means that this computation is to be done step by step. This computation is to be done by referring to small steps. How much they can be small? I would say it depends on the beach. It depends on the heterogeneity of the conditions that I discussed just before. The step may be 10 meters. The step may be 100 meters. If you see that the geometry of the beach doesn't change much, 100 meters may be fine. If you see that the geometry and the wave behaviors are continuously changing, you may refer to 10 meters. You know, by referring to small steps, you may think that the computation becomes more cumbersome, more difficult. This is not true. I mean, you don't have to be concerned by the computational requirements. First, keep in mind that the theory, the concept, doesn't become more difficult if you refer to a very local scale. Even if you refer to a scale of like 1 meter, the concept, the formula, the theory doesn't change, doesn't become more complicated. You may say, yes, but I have to do more computation. Yeah, but you have now a computing power that is something that allows you to make a lot of computations. You don't have to be concerned by making 1 million computations. Once you understood how to make the computation, it's not a problem. Making a single one or making 1 million, it doesn't change anything. So what does really change when you refer to local condition? What really changes is the required information. Because if you want to define, for instance, the angle between the wave direction and the coastline every 10 meters, you need a survey of the coastline every 10 meters. And you need a monitoring of the waves every 10 meters. So the real problem is data. The real problem is the information. So you don't have to be concerned about computational requirements or, let's say, complexity of your approach, because, you know, complexity is something that can be resolved. Even if somebody asks you to apply a very complicated model, okay, you study the model and you apply it. It's not a problem. And the computational requirement, if one personal computer is not enough, you buy from Google computational power, which is given almost for free. And it's not a problem. You can run your computation on a server given by Google. Not a problem at all. What is really problematic is to get the information. If you need a survey of the beach, every 10 meters you want to get a point, every 10 meters you want to get a survey by the surveyor, then this is a problem. Because first of all, it costs a lot of money. And second, it takes time. It's not something that you can get with a click on the screen. And it is something that may require wave monitoring. Think about wave monitoring. You cannot resolve lack of data on waves in 1 month. You have to install a monitoring station, and then you have to run the monitoring station for at least 5 years, maybe. So you see that it's a bit of a problem. So you just have to be concerned by the information. This is your first question. When you are given a problem to resolve, the first question is data. Where do I find the data? Can I find the data? I mean, the other questions are something that an engineer can easily resolve. Now, let's suppose that we then applied this model. Okay, I am selecting again. Okay, we actually compute the evolving shape of the coastline, because this is what we are really interested in. I want to see how the coastline may evolve in time. Here, there is a sketch of a very simple model, and this very simple model is called the one-line model. Now, let me explain how it works. First of all, this is a very simplified model that was conceived when the computational resources were indeed a problem. I just said that computational resources are not a problem for you. But if you go back just, for instance, 20 years, it was a problem. It was a problem, the computation. There was no Google, almost no. I would say that 20 years ago, there was no Google. There was no availability, easy availability of servers, of public servers. So it was a problem. And this is the reason why the first models that were conceived were very simple. It was not lack of theory, it was lack of computational requirement, and maybe lack of data. So this model is very simple. Why it is called one line? Because it relies on a very simple assumption. It relies on the assumption that the shape of the beach doesn't change during the evolution, which means that the beach, look at this figure and look at where my mouse is placed. You see that the beach, in this case, moves back is the other direction, back, land side, and forth by keeping the direction of the coastline unchanged. The direction of the coastline, what I am browsing with the mouse, doesn't change. So let me better explain on the graphic, because I want to make sure that you get this. So just 1 second. Here we are. Give me 1 second, because it's a bit slow. Okay, let me take the black. So one line model. Let's suppose that you have a beach that is given by this shape. And you see that this is a shape that is given, this is land. I don't understand why it is continuously moving. This is land and this is offshore. Okay. This is a beach that looks like a sequence of segments. Why? Because when you get the survey from the topographer, the topographer doesn't give you a continuous line. It gives you, some points like this, etc. And these points are taken at fixed spatial steps. So for instance, this distance here is the distance delta x between points, and typically it is fixed. And this is the spatial step I was mentioning before. Okay, now let's suppose that this beach is subjected to accretion. Accretion means that it's the opposite of erosion. So let me take the blue again. So let's suppose that we have accretion. Okay, accretion, and let's suppose that accretion means that the beach moves in the offshore direction of a quantity that we called delta Xc. Now, it means that the new beach keeps the new coastline keeps the same orientation, and therefore, if you have an advance of delta Xc here, you have the same advance delta Xc here. It is identical. And even here. This is of course, it's an assumption which it's not necessarily satisfied, because actually, when you have erosion or accretion, the shape of the coastline may change. But the one-line model, again, one line, it's based on the assumption of same direction of the coastline. Good. So let's go back to the sketch that is on the website. Once that you work under this assumption, and once that you keep also the slope of the beach unchanged, you have completely defined the geometry of this yellow volume, because you keep again the direction of the coastline unchanged, and this is an implication of the one-line assumption. Also, again, the slope of the beach is unchanged. So you have completely defined the geometry of this yellow volume. The only unknown is delta Xi, yes, or delta Xi. And how to compute delta Xi with the knowledge of the volumetric transport rate, because if you have a Q entering into this yellow volume, which is the result of the application of the Csc formula, and then you get to the next step. In the next step, you apply again the Csc formula, and then you get another estimate of Q, which is the Q that goes out from this yellow volume. And therefore, you compute the difference. If Q in is greater than Q out, you have accretion. If Q in is lower than Q out, you have erosion. And then once that you estimated Q in minus Q out, this is the volume of the yellow shape that we define here. So the geometry is defined, the volume is defined, and then you can compute delta Xi. It is quite simple. We will make an exercise on this, which will help you to understand how this works. Basically, this is what I had to say about the Csc formula, one-line model, and a longshore sediment transport. And let me say that this is the most difficult concept that I am introducing during these 3 lectures. The remaining parts are more descriptive. Or there is another issue that I want to discuss with you, which is saltwater intrusion, which is a bit mathematical, but not as mathematical as this one. Now, I just wonder if you have any question, and let me share the screen so you can see me. Questions? I didn't check how many students, how many you are today. Let me see. 7, yes, fine. In order to get to a number of 10 for my survey, what I could do, if given that you are attending remotely, it is if you could spread the word with your colleagues. They would just need to connect next Friday at 3:45. We just need 3 more persons to get to 10. So if you can help me, I will send a message on the chat, but if you can help me with this, it would be much appreciated. Okay, let me go back to the chat. It seems that there are no questions. Good. Now let me again share the screen. And in particular, the web page. Very good. So, let's now move to another type of sediment transport, which is the cross-shore sediment transport. Remember, the cross-shore direction is the direction that is perpendicular to the shoreline or to the coastline. Alongshore, it's parallel. Okay, now, so far we spoke about the alongshore. First, what's the difference between the two? Of course, they are generated in a very different manner. And one important difference is that the cross-shore sediment transport is very impactful during storm events. So typically, the cross-shore dynamics is driven by extreme events. And it is, for this reason, very much changing depending on seasonality. The alongshore sediment transport is less related to extremes, is more related to an average situation. And so, what is the result? The result is that the cross-shore sediment transport evolves in time scales that are much shorter with respect to the alongshore component. So, in the long term, the shape of the beach is dominated by the longshore sediment transport, and this is also given by intuition, because if you consider that the longshore sediment transport, it is the real responsible driver of moving the beach from the mouth of the rivers to the remaining part of the coast. So the river brings the beach in a very local position, and then you need a driving force that is distributing the sand. Sorry, I said beach, but I meant to say sand. So the river brings the sand to a very local position, and then you need a driving force that moves the sand along the coastline to reach the other beaches. And this is a long-term shaping, a long-term process, which distributes, again, the sand along the coastline, even to a considerable distance. Instead, the storms, the extreme events, are responsible of very sudden changes that are basically local, and they may be responsible, these extreme events, of very significant erosion, and erosion that typically, given that it's cross-shore, a cross-shore process, it's an erosion that turns into eroding the land and bringing the sand into the ocean. And it may reach also a considerable distance. Now, how to estimate, how to model these phenomena of cross-shore sediment transport? It is more complicated. It is more complicated because you know, it's a process that evolves, as we said, in a short time scale. It is characterized by a lot of turbulence, and so for this reason, it's something that requires a deeper inspection. And it is a process that does not lend itself very easily to mathematical modeling. And this is why, for this reason, you know, very often when we have to analyze these processes in detail, we refer to lab experiments. I want to show you a video, which is, I think it is linked somewhere here. Let me check where it is, which is, I think it is very instructive. Let me just browse here, this video. I'm showing the video on my screen. If you see that the video is slow, you may just click on the link on your local PC. So let's see the video, because I think it is very instructive. And before looking at the video, let's look at the caption. Let me just stop it for a while, and let's read the caption. My PC is a bit slow, so be patient a little bit. Okay, still working. Okay. So before starting the video, okay, good. Let me see. I think there is. Sorry. Let's close this pop-up. Good. Let me go back to my web page. Let me stop it. Good. Let me go back to the web page, because there is in the web page the caption that I can't find here. So let's read what is the video presenting. So the first part of the video is 2 hours. It's 2 hours in the natural time scale. Keep in mind that when you make a lab experiment with a small scale model, which means that you reproduce what is happening in a smaller geometrical scale. When you reduce the geometric scale of an environment, you also change the time scale. This is something that comes from the theory of small scale models. We are not interested in inspecting the theory. I just want you to understand and to know that when you change the geometry and you build a small scale model, you also change the time scale. So it means that 2 hours in the prototype, so 2 hours in the reality, are reproduced into few seconds into the model. So you see that the first part of the video is 2 hours of 12.4 centimeter waves with a period of 1.3 seconds. These steep waves produce large destructive forces. Destructive means erosion on the beach slope. The beach's response, the beaches is flattening out, and basically it flattens by slowly eroding the berm. We will see in the video, the dry portion of the beach. The berm is, you can also call it the dry portion of the beach. The eroded sediment is then transported offshore and built up as sandbars. Good. This is something that we already discussed from a qualitative point of view. Sand continues to erode, flattening the beach until the wave machine is stopped. Okay, the wave period is then changed, and the height kept roughly the same, but producing longer, more gradual waves. These waves lasted 3 hours and 15 minutes and were 12 centimeters height at 3.1 seconds of period. This longer period waves produced more constructive forces. Constructive means accretion of the beach, the opposite of erosion, which result in the sand from the bar being transported in a ridge and runnel system on shore. Okay, let's look at the video now. It's already here. let me just, let me see if I can put it full screen. Yeah, interesting. And now let me start it. So let's see what happens. You see the destructive forces. Beach is flattening out, and then a bar is forming offshore. You see that the video is accelerated, so just 1 second. Again, the bar forming offshore, video accelerated. Let's see now what happens. Now the period is changed. You see constructive forces. Just 1 second because it's a bit slow, my PC. Constructive forces. The bar is brought back into the beach. I think this video is an excellent example of how cross-shore sediment transport works. Okay. Now let me cancel this. Okay, good. And let me go back to the web page. Now, again, let me recollect what I was saying. Lab experiments. Why? Because when the phenomena are dominated by turbulence, are dominated by scale processes, the theory, the numerical modeling becomes less effective. And in this case, you have two options: either to rely on heavy simplifying assumptions, which are heavier than the situation that we experienced with the longshore sediment transport, which means that the model becomes a rough approximation. So either you rely on as I said, on heavy simplification, or you make a lab experiment. The lab experiment is something that is extremely useful, frequently adopted. There are international research centers in coastal engineering that are available to make large-scale experiments. Of course, these experiments are very costly, are expensive, especially if you make a large-scale experiment, because one thing is a flume, another thing is a pool. And for instance, I'm sorry that I can't bring you in our lab in Bologna. In Bologna, we have a lab where we have a pool where we make lab experiments, quite large-scale experiments, with waves and sediment transport. Now, I think it is anyway useful in this short treatment that we have to do, in this short time that we have available to discuss. I think it is useful to see in a qualitative way what happens. And this sketch here, it's an end-of-written sketch, which is a bit, I mean, it's a bit rough, but I think you can understand the concept. This is depicting what we just saw in the video. So what happens when you have a storm in the cross-shore direction? What happens is that the beach flattens out and a bar is formed into the sea. This is a typical situation when you have a classical beach with a berm. You see here we have the berm. This is average sea level. And then we have this swoosh zone here. It is the steep part of the beach above the average sea level. Look at my mouse. And then we have the berm here. There might be the runnel here. The runnel is, as I said, a kind of channel with salt water located between the berm and the dune. And then we have the dune. This is a classical beach. And if you get a storm, the situation that you get may be this one, the post-storm profile. And then, if you have mild conditions prevailing for a long time, it may happen that the bar is brought back to the position of the berm, like we saw in the video. So it is extremely important that we have conceptual understanding of what's happening, of what's going on, because this allows you to predict the output from your experiment. It may be a numerical experiment, it may be a lab experiment, it is important to be able to predict the result, to get an idea, because if you are able to get this idea, then you are also able to judge whether your experiment, your model is working well. And this is the result of what is frequently called experience. And keep in mind that experience doesn't need necessarily time to be gained. Experience means knowledge. And the knowledge can be acquired even in a short time. If you are a good student, if you are a good engineer, your knowledge is acquired in a short time. And you don't need to become white-haired like me in order to claim that you have knowledge and you have experience. You just need to be motivated. You just need to be very enthusiastic. You just need to like what you're studying, and you just need to study, of course. Now, this is a typical situation. Let's see another situation, which is the evolution of the beach profile triggered by a sea level rise. This is a situation that today is considered to be very interesting, because you know that the sea level is rising for the effect of global warming and the melting of part of the ice caps. And so what happens when the sea level increases? Of course, you need to reach a different equilibrium situation. If the sea level is increased and then remains stable for a long time, you reach a new situation, which is given by the dashed line that you see in the figure, and which means that part of the berm is eroded. The berm is placed a little bit, it's a little bit shifted landward, which means that the dune will also be shifted a little bit landward, and part of the sand is transported in the offshore direction by forming a bar. And now let's see what happens with the beach nourishment. Beach nourishment, as we will see, is an intervention that is frequently adopted when we want a contrast beach erosion. And what happens is that if you start from an immediately post-nourishment profile, then this profile is typically modeled by the action of the waves, and to reach a stable slope. And the stable slope it is frequently milder than the slope that we give to the post-nourishment profile. And the reason is that we typically want to be resilient in our design. So we typically tend to put more sand after nourishment, and we give a slope to the beach which is higher than the equilibrium slope, because in this way we converge quickly to the equilibrium profile. And then the last sketch is what happens with the construction of a seawall. And this is another important situation to know, because what you have to know is that when you build a seawall, you induce erosion at the foot of the wall. And this is explained by the fact that the waves that go hit the seawall, they go against the seawall, against the wall, originate a turbulence against the wall, which travels up and down, and therefore you have part of the wave that goes in the direction of the seabed by originating turbulence at the contact point between the wall and the seabed. And therefore, you obtain the fact that you dig a kind of hole at the foot of the seawall. And it's important to be able to predict this, because you have to put the foundation of the seawall at a proper depth in order to avoid that the foundation, of course, the stability of the foundation is undermined by the erosion. So these are simple sketches that allows you to understand what happens in typical situations, which we may experience with a frequency that is relatively higher with respect to others. And what I suggest you is to try to figure out how the movement of water is shaped by a given intervention, or is shaped by, for instance, an extreme event, and to try to figure out in which direction the water moves. And when you have water moving at a considerable velocity, then you have energy, which means transportation of sediments. And if you are able to figure out in which direction the water moves, you are also able to predict what is going to happen after the action of waves. First of all, let me also say, not first of all, let me also conclude by saying that there are empirical criteria that have been proposed by the literature to try to decipher, to understand the shape that a beach will take under the action of extreme events, under the action of waves in general, and after given human interventions. As an example, here I am presenting a criteria, the Tsunamura and Horikawa criteria, to determine when we have accretion rather than erosion. So let's look at this very empirical relationship, which anyway may be really important, because empirical relationships are very useful to get an order of magnitude, to get a first understanding of what happens. So it is, and they are useful also because they are easy to use and quick to use. So it is important that you get a panorama, a full picture of the empirical relationship that may help you, because usually they are not to be used for the final design, of course, because they are too uncertain. But in order to elaborate your strategy, in order to get a first picture of what is needed to resolve a particular problem, I actually found that they are very useful. So let's look at this relationship here. Here, H0 and L0 are wave height and sorry, I didn't turn the phone off. Be patient. Okay, and again, H0 is wave height, L0 is length in deep water, which means basically the sea depth. And here, beta is the beach slope, and the D50 is the grain diameter of the beach particle, such that 50% of a sample mass is smaller than. I think you understand what D50 means, because I'm sure that you already discussed the ways and the methods we can use to characterize the size of sediments. So I think you already know what D50 is. If you have any doubt, just write on the chat or let me know. And just let me check if, yeah, nothing in the chat, okay. So in this relationship here, K is a constant, and so when the left-hand side of this formula prevails, you have erosion. When you have the equal sign working fine, you have equilibrium. When the right-hand side prevails, you have accretion. So as you see, it is extremely easy to apply, and maybe a good support in order to get a first understanding, as I say, because sometimes you are brought into a beach and okay, there might be erosion, but you don't know at a first glance the intensity of such erosion, and an empirical relationship may really help you to understand if the beach is close to equilibrium or is far from equilibrium. Okay, now here there is a discussion on in my webpage on constructive force and destructive forces. It is a discussion that helps you to understand, especially in open sea, why the particle of sediments move, because it is easy to understand how and why the particles move after the breaking of the waves. It's clear there is a movement of mass and the particles are eroded by the moving mass, and they are transported by the flow of this mass. So it is relatively easy. It is not so easy to understand how the movement of particles may take place at the sea bottom in open sea. It is something that actually happens, and given that the waves, especially close to the sea bottom, should not involve any movement of fluid, but only a movement of energy, one may wonder how the particles are eroded. And the reason is that actually, even if in the deep sea, you have the particles of fluid that are really nearly not moving back and forth. They are just moving up and down. And also the movement, the up and down movement is very reduced in deep sea. It is not so easy to understand how this may translate in some sediment transport. The reason is that close to the bottom, where the sediments are, you have an interaction with the seabed. And in this interaction, there are some movement of fluid that are originated. So, in fact, the interaction with the bottom gives rise in the vicinity of the bottom, in the so-called boundary layer, gives rise to a movement of fluid, which is given by the fact that there is some energy that is lost in correspondence of the sea bottom for friction, and this reduction of energy gives rise to a movement of fluid. It is a consideration that I wanted to report here in order to give you an idea also of the complexity of this process, and in order to give you an explanation of why these particles are moving, even if the waves before breaking shouldn't originate any movement of water. Anyway, this is just a consideration that I leave you to read. These are details that I don't ask at the exam. I may ask at the exam how the Csc formula is derived and what are the assumptions of the one-line model and how we can numerically compute by using the one-line model and the theory the evolution of the beach. But these details that are more, let's say, descriptive, I'm not asking any question. Now, it is 3:45. Let me see if Professor Bratt joined us. 1 second. And I see that there is a question, but let me just check. If we have some time to wait, we can.
Alberto,
yes. Yeah, Alessio.
Ale.
Yeah.
Hi,
okay.
everyone. Professor Bratt couldn't make the survey today, so I'm replacing Professor.
Okay, because I see that Armando is in. No, it's not here. Okay, fine. Yeah. So let me just, Alessio, give me 1 second. So
absolutely,
students,
no problem. I'm here. I'm following. So when you're ready, tell me. Okay.
Okay. So students, I see that there is an hand raised. Please. No, it's Alessio. Okay, very good, perfect. Okay, Alessio. So if you have any question, please. Write on the chat. I give now the word to Alessio, and I'm making my break. So I think we can restart the lecture at, let's say, let's take 5 minutes more, because there is also the survey. I want to give you students also some break. So let's meet again at 4:05. Alessio.
Okay. Yes, Alberto, can I just ask you one simple question? I need to know how many students are actually attending. I think I see 13 plus 6,
no,
right? Is it correct?
No, I don't think so. I think they are 7. Because
okay, just 7.
No, 6, 7
because minus me, so it's 6, right?
Yes,
so
because the other students are not present today.
Okay.
So I think you have to get the survey from these 6, because another possible solution could be that you leave the survey open and send a message on the chat by saying to the students that you are closing the survey maybe tonight. Okay, so you give to the other students the opportunity to complete the survey up to midnight. This could be a possible solution, and if you I think this may be advisable. And then you write a message on the chat by inviting students to fill the survey. You give the instruction, and we kindly ask the students that are attending now to bring the word to their colleagues. Okay, I think I give you to promote you to presenter. Just 1 second. 1 second, because it's slow.
Yes.
Make geometry to the geometry of a considered system, in this case the beach, after a movement of sediment. This is a very general equation. It is applied in the modeling of river beds. It can also be applied in the modeling of the morphology of beaches. It's called the Xner Equation. It is using a concept that is similar to what we saw for the one-line model. Basically, it says that the partial derivative of the bed aggradation, so it's the partial derivative of the vertical dimension of the beach. So let's suppose that h is here the elevation of the seabed with respect to a reference plane, to a reference horizontal plane. So the partial derivative of the elevation of the seabed with respect to time is equivalent, upward positive, is equivalent to the partial derivative with respect with respect to the cross-shore direction of the flux of crossing shore sediments. So if you estimate the flux, the volumetric flux in the cross-shore direction of sediments, if you make the derivative of this flux with respect to the cross-shore direction, so let's suppose that x is positive landward. If you have a decrease of flux of sediment in the cross-shore direction, it means that you have a deposition of sediments as you move in the same cross-shore direction. And this deposition is, of course, causing an accretion, an increased elevation of the seabed during time. So by just equating in differential terms, the change in the fluxes of sediment along x, this equation is computing the changes in bed elevation. It is the same reasoning that we did for the one-line model in the along-shore direction. For the one-line model, we made the same reasoning in finite difference terms. We used the delta, not the partial derivatives. This equation, again, it is something that I'm not asking at the exam, but I think it is important that you know this name, the Xner equation. When it is used when I want to model the geometry, the change in the geometry of a given system, in this case a beach, has a consequence of a flux of sediment, and in particular changes along space of this flux of sediment. And this is what I wanted just you to know, because the name, this equation is very well known. It's like in fluid dynamics, the Xner equation, for instance, or the Navier-Stokes equation. These are equations that are very well known. They represent, in a way, pillars in the theory, in this case, of morphodynamics of beaches and rivers. And they are pillars, and therefore it is something that you should know, at least by name, and at least in the main, you need to know the main picture. So what they are, what they refer to. Okay, this is the conclusion of our discussion, of our brainstorming on beach hydrodynamics and morphodynamics. Again, any question?
For me, it's all clear, Prof. Thank you.
Okay, thank you. And if it is too clear, you just have to let me know. I mean, as I already mentioned to you, I'm really interested in your feedback. If I am too fast or too slow, I'm interested in knowing. Okay, now let's move to the exercise. And let me make a premise. As I mentioned to you last Friday, I want to dedicate some time to exercises, practical exercises. The reason why they are useful, it is trivial, because if you practice what you studied, of course, you learn much better. On the other hand, I think it is also useful because it gives us the opportunity to learn a new software, to learn a new tool, something that you may use in your profession in the future. And as I think I already mentioned to you, it is very important that you build this essential part of your CV, so your knowledge of tools. We may have different categories of tools, digital tools, also called digital literacy, and other tools may be technical tools, like instrument that you can use in the lab, or instrument that you can use to monitor, for instance, the waves. So it is extremely important that you have an overview of these tools. And in terms of software, the software is today, of course, extremely important for obvious reasons. And I think it is then important as well that you get acquainted, that you get knowledge with a set of softwares that may be useful to you. And this is something that you can put in your CV. So for instance, I think you saw some examples of CV where there is a section, and in the European format of the CV, there is explicitly a section which is called computer skills, which means that you list there the programs that you are that you know, and the programs that you have experience to use. So it is important, for instance, many people put, even if it is somehow trivial, good knowledge of the Microsoft Office suite. Or other people put good knowledge of AutoCAD, good knowledge of MATLAB. And it is extremely important. I think that the more you know and the more you can list in your CV, and the more opportunities you may gain. I believe it is especially important at the beginning of your career, because, of course, at the beginning of your career, you cannot list other set of experiences. You don't have a large set of experiences that you may list. And for this reason, I think it is important that those experiences that you had the opportunity to exploit are introduced and explained in detail. So again, this few hours of exercises that we will make together will give us the opportunity, I think, to learn also a new software. In fact, the software that I want to use with you, it is a computational software. It's a software that allows us to make computation and to write programs. Writing programs is another skill that I think it is important that you acquire, because in your profession, as you will see, you will find some challenges in your everyday activities which cannot be easily solved by using commercial software. In many cases, it becomes more practical to develop your own program, your own software. So programming is another skill that I highly suggest you to acquire. So this software is, again, a computational software. It is somehow similar to MATLAB. With respect to MATLAB, I think you can do more or less the same things. With respect to MATLAB, it has interesting feature. It is open source. Open source means you have to spend money to buy it. It is available for free. And this is not only an economic advantage. When a software is open source, okay, you have the economic advantage, which in your condition of students is not very relevant because MATLAB for you is basically available for free if you're using it inside the campus. But once you are not a student anymore, MATLAB is somehow costly, and therefore it may become also an interesting advantage, also the economic issue, the economic side of it. But what is more interesting, I think, is that your results can be shared and your program can be shared without any obstacle. And you know that today data sharing, information sharing, code sharing is considered to be essential for moving forward. So the fact that you are free to share what you create, what you are free to share your ideas, your innovative ideas, it's indeed something that may be very important to you. And another thing is that when a software is free, you can get support more easily. And there is a community of free users that is always ready to help you. So I think indeed getting more and more experienced with free software, it's an extremely important issue. Of course, the first step that we have to make together is to learn something about the software and to learn the basics. And we have to learn very quickly because we don't have much time. So we have time today. I plan to dedicate maybe 1 hour next Friday, but not more. And therefore, what we can discover together is just a breadcrumb. It's a small piece of what this software may mean to you. And for this reason, I think it is important that on one hand, you pay attention. On the other hand, we try to be very efficient, to get to target very quickly. And of course, if you're interested, you will have time in the future to learn more and to study more. One additional advantage of the free software is that free study, independent study, is much easier, precisely because you may have extended support from the community. So what is this software? So I suggest that we install it together. I think in this PC may be already installed. Just let me make a check to see if it's already installed. Maybe not. Let's see. Okay, perfect. So we can install it together. Before I start, I am a Linux user. We will have a discussion about different operating systems maybe later. I suppose that you are not a Linux user because Linux users are not frequent. You are probably a Windows user or a Mac user. So can I just make a brief, I think you are 6 students. This is very quick. Can you please write on the chat if you are not a Windows user? If I don't read everything, it means that you have Windows. If you have a Mac, please write on the chat, I have a Mac. If you have a Linux, just write on the chat, I have a Linux. 10 seconds. Okay, I think you all have Windows, which is fine. So as I said, I have Linux. So I have Windows 10. Yes, very good. As I said, I have Linux. So what you see on my screen is different from what you will get on your screen, but not much different. First of all, where to download the software? Let's open. Oops, I opened not a web page as I wanted to do, but I open. Just give me 1 second to close it. I opened the mailer. Just 1 second. Okay, let's close this. Good. And let me open a web window. And let's go to Google here. This is a Google page, and let's look for our project with the dash. Our project with the dash. Let's forget about what you see. It is suggested on my screen. Of course, I already searched it, so I get suggestions. Our project, and then return. And you see that the first item is the R project for statistical computing. Actually, this is not a program for statistical computer, or let's say, not only. It was born and it was created with the purpose of making computational statistics, but then it was extended. So don't get concerned. I know that some of students are concerned when they see the word statistics or probability. So don't get concerned at all. Very good. So let's click on it. The R project for statistical computing, and we get to this web page, and this is the same for everybody. So first, let me expand a little bit the font, and let's look at documentation, manuals. Click on manuals. Okay, and then there is this manual, an introduction to R. Download it. We don't use it today. I just want to tell you that this is very useful, and it's a short manual, so you can refer to R release, refer to, for instance, to the PDF, and you download it, and you keep it in your PC. So this is one thing. Let me go back. As I said, the manual is not to be used today. Download here. Good. Let's click on the only link that you see under download, CRAN. If you get lost for some reason, please write on the chat by keeping into account that I don't see the chat continuously. So if you get tremendously lost and you get into panic, just step in with the microphone and say, please, I missed this, and this. Okay, no problem at all. We are working together. Maybe that I also get lost because now I am installing it as you are. So, I mean, it's not a problem. So now you get this page with a series of links. They are all mirrors. Just select the closest to you. I mean, it doesn't make any difference nowadays with the speed of the web that everyone has. Just click, for instance, on Austria. And then here you see download R for Windows. Very good. Let's click on download R for Windows. Good. You see that there is a list of 4 packages. You are interested only in the first one, Bayes. Look here, binaries for Bayes distribution. This is what you want to install R for the first time. Perfect. Bayes. Click on Bayes. Download R for Windows. Again, click here in the first link. Download R 4.0.3 for Windows. Good. Let's click there, and you get the executable file. You can save it, or you can directly open it with the installer. Sorry. Let's suppose that you save it. So you save the file, okay, and then a download starts. At the end of the story, in your download folder, you find the installer. You see it is a exe file. You double click on it and you get it installed. I cannot double click on it because I am not under Windows, so I cannot show you what happens here. But again, once you downloaded it, go to the download folder and double click on it. And then you will be asked some questions. Select the default installation. Don't select any custom option. Just take the default, answer yes to the questions, and then you will get the program installed. After this, please start it. Okay, now I am moving forward under Linux. Again, different procedure. after starting my program, I will wait for you to make sure that everybody of you was able to download the program, install it, and start it. Okay? You can look at the screen if you want to see what I do, but actually it's not very useful for you because, as I said, it's a different operating system. So now I am downloading and installing give me some minutes, and also you will need some time. I have almost finished. Just be patient a little bit. Unfortunately, as I said today, my connection is not so strong. I am taking some time now to close the other windows, and it's moving forward. Okay, now I am starting the program, and I also think I need to change the fonts. 1 second. So let me colors. Okay, here. Let me use 15. Okay. So if you were successful to start your program, you should get to a window which is similar to what you see on my screen. It is a bit different because you have under Windows, you also have the menus, which I don't have. But you should find, in a way, a white window with a major sign, a greater sign, like this, and these lines of instructions above. So let me look at the chat 1 second. Can you please write on the chat if you still have problems in getting it installed? I'm waiting for some time for feedback because I want to make sure that everybody is able to follow me. So it looks, let me see, still installing. Okay, let's wait a little bit. And if it is just a matter of waiting, it's not a problem. If you want some help because maybe that you are experiencing problems, and this is what I'm saying is addressed to everybody, just let me know and we can discuss together. Okay. So while we wait for you, for the others, I just a brief done. Okay, very good. So a brief introduction. If you press Ctrl plus L together, you clear the screen. Okay, good. Now, you see, this is a console. A console is means that it is the PC is waiting for your input. You see, there is this sign of greater than, or and after the sign is used by the program to identify the input line. And then you have the cursor, which is the black rectangle. The black rectangle is the cursor, which means that it is the place where the input is waited for. Let me say that this program, like like MATLAB, allows you, as I said, to make computations like Excel. Excel is similar. It's also a software that allows you to make computations, but there is a difference. Excel is user-friendly, and being user-friendly, there is an help that is very detailed, and everything can be done by using menus and windows. It is easier because with the menus and the windows, you can see all the options that you have. So the menus and the windows that you open by using the menus are in a way already a user manual, because you click, for instance, in Excel on File, and you see all the options. And this means that the program is user-friendly. And also, with Excel, you would say that it's window-based, meaning that you use the mouse, you navigate through windows that you open by clicking in options that are listed in each window. And this means that it is a kind of guidance. But the fact that, just 1 second, because I see that there is a lack of connection, just 1 second. Can you please just confirm to me that you are still listening to me? Yeah, I think so. Can you please confirm?
Yes.
Okay, thank you. And sorry for that, but I got from the phone a message that was not clear. Okay, so as I said, the fact that a program is user-friendly has a downside, and the downside is lack of flexibility. So Excel works with windows, giving you options. But if you want to go out of these options, it is a problem, because it doesn't allow you to. Because it doesn't allow you to personalize in an extensive way what you see in the windows. So user-friendliness implies a reduction of flexibility. This is why some programs which are intended for a higher level user, they are less user-friendly because you gain in flexibility. So basically, in R, you have the problem that you don't know what to do with this command line. You know that the PC is waiting for your input, but what kind of input? What kind of input can I give? Can I give, I don't know, relationships? Can I give instructions? Can I give numbers? You don't know. In Excel, it's much clearer because you have the windows guiding you. Here, you have to know what are your possible options. And given that these options are widely extended because the program is highly flexible, it becomes a little bit difficult to learn all the options that you may have. So, in a way, I think it is a step that is worth doing because you are a higher level user. You are not the kind of user that Excel and Windows are intended for. Excel and Windows are programs that are intended for giving the opportunity to everybody to use the PC. For high-profile users, there are other programs, and you are definitely a high-profile user. So this step is worth doing to understand what is the trade-off, because between user-friendliness and flexibility is a step that is worth doing. And learning how to use a program that is not user-friendly is for sure worth doing. But how to make it efficiently, how to get oriented in this wide perspective. First, you don't need to learn all the things that a program allows you to do. With R is almost impossible. I think I know 1% of the programs that can be done within R, maybe less than that. So we just need to learn what is useful for us. This is the first premise. And the second, given that we need to be very efficient, I suggest that we use a very practical approach and a kind of holistic approach. Let's move forward empirically by starting to learn what we need, what we strictly need. We need to make an exercise. We need to compute the evolution of a beach. This is our exercise. Let's learn only the instruction that allows us to use to make a program that computes the evolution of a beach. Perfect. So let's move forward step by step. First thing to do is to learn how to make computations. Let's start from 2 plus 2. I write 2 plus 2 on my command line. I press return and I get 4. Amazing, okay? I can also write 2 times 5, 10. So I can make the 4 operation, 2 divided by 4, 0.5, and I can combine them. 5 minus 3 times 7. minus 16. I can use parentheses. 5 minus 3, close parenthesis, times 7, 14. I can also use other elementary computations like elevation to a power, 2 hat 3, 2 to the power of 3, 8. Or I can compute the square root of 4, 4 to the power of 0.5, 2. Good. So we can make the 4 operations. We can make a very complex command line, line 2 times 3 minus 4 minus 5 plus 2 to the power of 10 and times 2 minus 4 divided by 8, etc. You can go forever, and you get at the end the result. Okay, this is not really useful so far. Let me clear the screen and let's make a step forward. What about more complicated computations, like, for instance, log exp 4? I guess the result is 4. Perfect. So let's see what I did. First, let's focus on the log. Log of a number between parentheses. Why? Because this is not a basic operation. This is a function. This is application of a function. A function has arguments, and the arguments are to be given between round parentheses. So if I wrote something like log 4, I would get an error. Log, what is the argument? It's a number, 4. I need to give it between round parentheses. What I computed at the top of the screen, log exp 4. First, let me get it back. In order to get it back, I can use the arrow up key. If I use arrow up, I go back in my previous history. Now I am pressing arrow up. You see? Now let me press arrow down. Down now. I move forward from the point where I got with the arrow up. Up to the end. Okay, let me use again arrow up. I want to get back log exp 4. Here I am. This is a combination of two functions, logarithm and exponential. And you see that the argument is always given to parentheses. In this case, the argument of the logarithm is another function. No problem at all. I can even write log exp log exp 4. Now I have to remember how many parentheses I have to close. 4. 1, 2, 3, 4. Okay. So you may ask me, how many functions do we have available? Too many to be learned. We cannot learn all of them. What I suggest you is, once you need a function, look for help. How to look for help. I suggest you a very easy way and very rapid way. Let's suppose that you don't know how to compute a logarithm with base 10 in R, okay? Because this log here, it's of course log in base E. You see, I compute log 4. If I compute log 10, you see the result is 2.30. What should I use if I want to compute the logarithm in base 10? Okay. Let's take a internet window, a web window, and let's go to Google. Just 1 second here. Let's go to Google, and then let's write R project log base 10. Let's see what happens. Let's click on the first link, log function. Good. click on log function. Oh, this is what I was looking for. Log usage, log x base. There is a second argument. This is good to know. I didn't know this. So there is a second argument, which is the base. Good. Now, let me go back to R and try, okay? I go back to R. Sorry, here it is. So let me clear the screen. Here is my console. Log 10, comma, base equal 10. Perfect. This is what I wanted to know. Actually, let's go back now to better understand. Let's go back to the web page. Let's go back to it. So what I see here is that there is additional information. I learn from here that there are two arguments of the log function. One is x. The second is the base, okay. But I see something more. For the base, there is a default. And the default is a default value for the base, which is precisely the number e. Exponential 1 is the number e. Which means that if you don't specify the base, you get the default. The same is not true for x. X doesn't have any default, so you need to specify it. So for instance, if I go back to R and I make log without giving any argument, you see the error argument x is missing with no default. But if I write log 10, I don't get an error because the second argument, which is the base, has a default. From the help, I go back to the web page. I also see that there is another function called log10, which I could use. Let's try. Log 10, 10. 1. Very good. This is perfect. Now, this help, it could be found also here in R. What you find on the web, what I found on the web, it's also embedded into R. How to find it? Well, you have to know the name of the function, and then you write a question mark followed by no space with the name of the function you want the help for, and see what happens. We get the same information that we got from the web page. Perfect. This is another way of finding help, but in this case, again, you need to know the name of the function. If you search on Google, you could have used another keywords like logarithm, and you would find the same page. In R, if you use a keyword that is not, let's go out from this help by pressing on Q. Here, if I write question mark logarithm, maybe that it is not, yeah, okay, let's say logarithm, you see that there is no documentation. And with logarithm, it's the same. And it tells you, you can try with double question mark logarithm, but you don't get very useful information from this because it gives you usually an information that is not ready to be used. Okay, now let's move a step forward because we need to be very efficient. So let's go back to our console and let's see how we can assign variables. A equal 2. Nothing happens, but now if we write 2 times A, sorry, A, we get 4 because we have assigned a number to a variable. How to get the list of the variables that we assigned? List, do you have any question? List, ls, lists this function ls with no arguments because there are defaults already specified, gives to you a list of the variables that you defined. Very good. So you can write b equal 10 and then write numerical expressions, b divided by a, for instance, 5. You can remove the variables by writing remove rm a. And then if you write a, there is object a not found. B is still there. If you write b, you get the value of 10. Okay, so we learned how to make computation, how to assign variables, how to how to use functions and find the help for them. Another step forward, vectors. So very often we need to define vectors. So the vector is defined in this way. A equal, we need a function to define a vector. And the function is just a function c. And the arguments are the elements of the vector, 2, 3, 4, 5, 6. Now, if you write a, you get the numbers into the vector. And if you want to get a single element, is to be given the index between square parentheses. And you can make operations with the vector. A times 2, you get a multiplication by 2 of each element of the vector. Okay. You can make more operations on the vectors, but let's now forget about it. I just suggest you to practice. For instance, if you make a plus 1, what you obtain is the addition of 1 to any element of the vector. And but if you define a second vector, b equal, and 5 numbers, 10, 20, 30, 40, 50. Oops, I forgot to put c here. And then you write a times b. You get something that is the multiplication. You get another vector, first of all, and the other vector is the multiplication of each element of the vector for the corresponding element of the other vector, which is not really intuitive. You have to make experiments to get experience in how R works. I think MATLAB works in the same way, but there might be differences anyway when you go to details. Okay. Now, you may define several variables, vectors, etc., etc. At a certain point, you may be concerned by losing data, and therefore to save what you're doing. This is extremely important. In Excel, it is very easy. You click on the icon of the disk and you save it. Here, you need to be more, it is a bit more complicated. So there are two things that you may want to save: the data, variables, vectors, and the history. Also, the history is very important. So let's start with the history. The command is, I think, if I will remember, save history with empty parentheses. Okay, perfect. It has been saved. And for in the data, I think it is saved at image. Yes. Another suggestion, sometimes I don't remember the name of the functions. And in order to make sure that I don't make mistakes, because, for instance, if I write just save, I'm not sure what happens. You see that there is something wrong here. So in order to get assistance, what I did is to write save, and then at this point, one may not remember if the command is save or save image. A possible solution is that you push the tab button twice, and you get a list from R of all the options. So if you still don't remember, you can look for the help of each one. But in this case, I remember that is save image, what I need. And then I put a dot here, again the tab button, and I get the completion of the name of the function automatically. This allows you to save time. By the way, saving time is extremely important. When you work with the PC, it is amazingly easy to get lost and spend one day in doing nothing, a full day. And so it is important to learn how to avoid this, and how to save data, how to protect yourself against digital risks, how to become efficient when you use the PC. It is extremely important. Okay, saving everything, it is particularly important because in R, there is no undo. And so, I mean, if you make a mistake or your computer crashes and you didn't save, or you made a mistake and deleted everything, there is no possibility to undo the mistake. And therefore, it is important to save the history and to save the image. To save the history is important because you can repeat everything you did. So, for instance, let me show you the power of the history. If I just write history here with no argument, you see I get the full list, it's not really full, of what I did today. It is extremely useful. If I want to get the full list, I need to increase the number of entries, 100. This is the full list. This is the full list of what I did today, which is very interesting because you can save it with the command save history, which is perfect. Okay, one more thing. We saved something. Where did we save? Okay, it is extremely important to locate the files that you saved, because you may need to reload them. And if you don't locate the files, you cannot reload them. So you should have a menu called File, which I don't have. If you click on File, or you click on another menu item, because they are not many, you can check, you should get an option which is called something like Set Directory. And then if you click there, you get a list of the directories on your PC, and you can select the directory of your hard disk where to save the files, which is perfect. So you, for instance, may create a directory called First Exercise Professor Montanari, and you save your files there. And you upload any file that you may need there. This is something that I cannot show you because I have a different operating system. So I kindly ask you and suggest you to practice on this by yourself. Again, it is extremely important that you locate the files in a place that you know. Good. Now, at this stage, we know basically how to use basic tools in R, how to use variables, how to use vectors, how to compute functions on vectors and variables, how to save, how to get back to the previously saved file. By the way, I want to tell you one thing. If you go out from R, if you quit with the instruction queue with no arguments, I try to do it, you get a message, save workspace image. If you type yes, you automatically save history and image. So if I type yes here, I got I get out from it. And if I start again, this is again my starting page. And if I list the variables, I find A and B there. And if I go back with arrow up in the history, I find everything. This is again very useful. So basically, once that you set the working directory, if you start R again and you select as working directory the one where you save the file, they should be automatically uploaded, and you should find automatically the history. Otherwise, if you don't find them automatically, you can use a load function. I don't remember what is after load, so let me use the double tab. And you see here, I have load history. Load history is perfect, which means that I can load the history. And also there is the function load, which I think allows me to load my saved image, so variables and vectors. Let's see the help for load. Reloads dataset written with the function save. Actually, it's not like save image, but I think it can be used. Load, it can be used. So this is another thing that I leave you to practice. Okay, now I think it's time to open our exercise and see what we have to do. And then once that we knew what to do, we can move forward by learning additional things. So let me then pass to the exercise. I go to my web page actually here. This is the page of our course. Now let me go down. And you see here, there is a section called tutorial web page for the practical exercises. Oops, sorry. And here you have a short introduction to R and RStudio. Let's forget about RStudio for now. I don't think we will have the time to see together what is RStudio. RStudio is a platform, is an environment for using R, for creating some user friendliness. And it may be useful, but let's forget it for now. And there is a link to the manual, and there are some slides which were prepared by one of my previous assistants to explain how to use R. So we are not opening this link. It is something that I leave it to you. And exercise, application of the Csc formula. And there are other links. Let's see, data files reporting the geometry of the shoreline and the wave forcing. So as data, we have the geometry of the shoreline and the wave forcing. So here we have to apply the Csc formula and the one-line model. Example of R file, which this is very useful. Let's start from this. Of course, this is something that in normal applications in your professional life, you have not ready. It is something that I built. It is something that we should build together. I give you the example because it is an aid, of course. It is something that may help you. For sure, it helps you. So let's see the example of the R file. And as you see, there is a set of instructions. And the definition of variables, definition of vectors, it doesn't seem so complicated. Many of the things we already saw. Okay, so let's look now at the exercise then. This was just looking at the R file is just to give you an overview of what we have to do, of how the program looks for. Now let's read the exercise. It is a PDF. Let's open it with a document viewer, a PDF viewer. Of course, I am working with a different operating systems, so it suggests me a viewer that it's not the same as yours, but it doesn't matter. Whatever you click on it, whatever program you get, it allows you to to read the exercise, which is application of the Csc formula to study the evolution of the coastline. It is what we just learned to do. Okay, so let's read together the text. The geometry of a coastline is described by the coordinates along the x-axis given in the first column of this file here. This is a link that you have to put on the web to download this file. Okay. The second column reports the limiting geometry of the shoreline. What is the limiting geometry? Let's suppose that we get erosion and the erosion moves on. But there might be limits like a seawall. If you have a seawall in the land, then erosion stops when, of course, it gets against the seawall. So if you have a limiting configuration of the shoreline, then, of course, we need to take it into account. And it is given in the second column. Actually, we will not use it, but it is anyway useful. Okay. The coordinates along the y-axis are equally spaced with a step of 150 meters. We discussed what is the meaning of the step, while the time step is given here in days. Okay. The beach is subjected to a wave forcing that is described in the file here. And let's see what we find in the file. The first 3 rows of the file report the spatial step along the y-axis, the time step, and the length of the simulation in terms of time steps. The following 5 columns report the position of wave breaker line, not required for performing the simulation, in terms of distance from the corresponding x coordinates of the shoreline. Second column, the wave height at the breaker line. Third column, the wavelength at the breaker line. Fourth column, the sea bottom depth at the breaker line. Fifth column, the wave angle alpha with respect to the y-axis. And there is an explanation here of what is the meaning of that wave angle. And there is also a figure. Let's look at the figure before discussing this description. The student is kindly requested to run a simulation of the beach evolution along 1000 time steps. Okay, let's see the figure. So here we have the 2 coordinates, and the coastline is given in terms of coordinates x and y. The angle alpha is the angle of the wave direction with the y-axis. Keep in mind that we need a different angle to run the Csc formula. We need the acute angle, alpha 2 in blue, between the wave direction and the coastline. And then, basing on the knowledge of alpha, we need to compute alpha 2. And here you see how to compute it, because alpha is reported here as the angle between the vertical red dashed line and the wave direction. And here you see an angle alpha 1, which is also, it is reported twice. And then it becomes straightforward to compute alpha 2, but we will make the computation later on, I would say next Friday. So let's now keep in mind that we have this figure helping us to compute alpha 2, which is the angle that we need, as a function of alpha. And I suggest that you have a look before next Friday to this figure and you get some ideas, preliminary ideas on how to compute alpha 2. Just an information which I think is useful. The wave forcing, so the geometry of the beach is just fiction. I just invented it. The wave forcing is not fiction. I went on the website of a monitoring agency, a coastal monitoring agency in the United States, and I got a sample file. I made just a brief modification of some numbers in order to make them easier to use, but actually the file is what you see if you go on the website of a monitoring agency. And this is why in this file there are some data that we will not use, because I decided to leave them there even if we don't need them to apply the Csc formula. Very good. So now it's clear what we have to do. Basically, we should adopt as time step of our simulation the same time step of 150 meters along the y-axis that we see here. So we have to apply our CERC computation at each spatial step and each time step. So it will be a kind of, I would say, hundreds of computations, but you don't have to be concerned, because making, as I said, one computation, making 1 million doesn't make a big difference. Once that you made the program in R that makes the first computation, you just have to repeat it automatically to make the other computations. At this stage, we have like 15 minutes left. Let's go back to R. And let's start to solve this exercise. My suggestion is to look at the example file, because this is the most efficient solution. To start with something that is already done and repeat it. This is why when you download a new software, very often they give you a sample application, something that is already done, and you repeat it. And then once you successfully repeated what has been already done before, you are ready to make your new computation. So let's use the same approach. We get the sample R file that I prepared for you, and we repeat it. And repeating is very easy because we can just cut and paste. Okay, so we may need to open these links. I'm not really sure, but I think yes, to make also a cut and paste of the data. But let's start with the file. So I go back with the example of our file. Very good. And now we are ready to put these instructions into R. An R file is a set of R instructions to be executed in R. A list of instructions is already a program. So what you see on the screen is already a program. A program doesn't need to be necessarily difficult to make. It is just a sequence of instructions. And the usefulness of R is that it allows you precisely to run programs. You can also do it in Excel, but it's more difficult. Okay, first, let's note that we can put comments in our list of instructions in our program. The comment is to be preceded by an hashtag. So for instance, let me cut and paste the first two, lines. How to make cut and paste? These lines are commented, so I am expecting that R does nothing once I put these two instructions into R. As I said, how to make cut and paste? Good question. There are several options. One possible option, I think it is probably the quicker solution, is to go with the mouse over the selection that I made and press on the right button, copy. Let me make it again. First, I have to make the selection. How to make a selection? I think the easiest way is to go with the mouse at the beginning or the end of the selection, push the left button, keep it pressed, and go to the other side of the selection. And then you can release the mouse button. Okay, now with the right, copy. Very good. Now let's move to R. Let me clear the screen so we are more relaxed. And right mouse button, paste. Okay, it gives to me a warning, unsafe paste. Let's paste it anyway. I don't think you will get this warning. You see, nothing happened. Nothing happened. Because these lines are commented. Good. Now, let's go again to the R file. Let's take the first instruction. It defines a variable. It defines a variable. Let me copy it. Copy. And let's see what's written here. First, there is the definition of the variable. RHOS equal to 2650, 2650. And then there is a comment. Sediments mass density equal to 2650 kilograms per cubic meters. Okay, I already copied it. Copy. Let me put it into R. Paste. Very good. Now, if I write RH tab button to make it, tab button to make it quicker, I get the value of the variable that I just defined. Perfect. I go back to the sequence of instructions. Now, there is the definition of rho, seawater mass density. Look at this number. 1025, 1025 kilograms per cubic meter. This is the average mass density of seawater. Keep this number in mind. Seawater, of course, is heavier in terms of weight than fresh water. Not much heavier, but still a bit heavier. So the next line is the definition of the mass density of seawater. Then we have the definition of the gravity acceleration. We have the definition of the porosity. And here there is a bit of a discrepancy. You see that the porosity in the comment is given a different value than in the actual definition of the variable. Let's forget about it. It's not a big problem. And then there is the definition of the parameter K, which is the empirical parameter. And then there is the definition of the beach slope. And you see the comment says it is not used unless one uses other formulas. Okay, so, and then there is the definition of the D50, which is the beach grain diameter. It is not used. Okay, now we could cut and paste each of these definitions one by one, but actually we can make it quicker. Let me select all of them. Let me start from here. I select all of them. I make a copy. And then I can paste all of them in R. Probably R will give me a warning saying it is unsafe that you paste. This is a Linux warning. Don't worry about that. Let's see. Paste. You see that I get the warning. Let's say paste. And you see that there is everything went fine. And now, if I list the variables that I introduced so far, you see that I have A and B from the previous exercise. Let's forget about them. But I have also the list of the variables that I just introduced. You see this interesting opportunity of cutting and pasting several variables, several instructions at the same time. Okay. Now, back to the program. What do we see next? I think we can dedicate the last 5 minutes or so to this instruction, scan. What is scan? And you see here what is the comment, upload of the coastline geometry. Scan is a function. You can recognize the function because it is followed by the round parentheses. So scan, as the name suggests, it's probably a function to look into a file and upload what is inside the file. So first I need a file with the name coast.txt, and there is no comment on this, but it is the file of the coastline geometry. So we need to get the file of the coastline geometry and scan it. The file is on the website. Perfect. Now, this step of putting data into R, it is a bit delicate. It is not so straightforward. It's much easier to do it in Excel. Now let's learn how to do it. And an essential premise is that you set your working directory. So what I suggested to do just like 15 minutes ago, like discovering your menus, how to set the working directory and identify it, it is now an essential requirement for uploading this file, because this file, cost.txt, is to be placed into the working directory. Now, let's go back to the website and get the file from there. To the website, I think, let me open another window. It's already here. Just 1 second. It's a bit slow. Let me see. Coastal engineering. Here we are. Okay. And let's look at the exercise. Geometry of the shoreline. Let's click here. We have 2 columns. Okay. So first of all, let's note, when I clicked on the file, let's note that what I'm getting is a text file. I guess that you already know what is a text file, as opposed, for instance, to a Word file or an Excel file. It is a file format. The text file is a file format, and it has the nice advantage of being something universal. It's not formatted, so it's not nice to see, but it can be read by almost all the softwares. It can be read by Word, it can be read by Excel, it can be read by R, MATLAB, etc. So this is why in my website I decided to put the file in text form. Now we need to save it, and to save it, you can click on the web page. Save page has. Good. Now you see that it's already called cost.txt. I am saving it in my desktop because my working directory, I hope it is my desktop, I'm not really sure, but let's try. So I am saving it, save. The same thing you should do, but you should save it in your working directory that you previously selected. Good. Now let me go to R. At this stage, I can cut and paste here. T equals 0. T equals 0 is just the definition of the starting time of our simulation. And then let me also select the scan instruction. I click with the right, copy. Perfect. I go back to R. And let me paste. There is the usual warning. Now, in order to make sure that I'm not doing anything wrong, I want to make something that you shouldn't need to make. I want to give the full path here. And don't look at what I'm doing, because in principle, if you set your working directory, you shouldn't need to do this. Just 1 second, because okay, here I am. It is a bit slow for some reason. you can try to move forward to check if the file is uploaded. Okay. Let me see if it works. You see, this error that I got is due to the fact that the file was not saved in the working directory, so it cannot find it. So let me now change the working directory. Just 1 second. Okay, now you see that I got a message, read 40 items, which I think it is okay because let me see, PR1, the file that I just uploaded, it's a vector, and he got the 40 items that define the geometry of my coastline. Okay, at this stage, I decide to stop. I start again next time. So what should I do here in order not to lose anything? Save history. Okay. And let me clear my screen. I think you can see it anyway. So save image. Very good. Now I can quit. It asks me, you want to save? Okay, just to be safe, double safe, let me get yes. And I got out from R. Now, I suggest for the next time, first, if you didn't succeed in uploading the data, just try again. Try again until you get this stage. I would like next time to know if you succeeded in getting up to here, which would be already a quite interesting result, because it means that you already overcame some of the major obstacles, some of the major hiccups that you can find when you start with R. And if you have time, I suggest that you have a look at the following and just to understand what's done here. And next time, I would like to complete this exercise. It will take about 1 hour. And then we move forward with the lectures. And there is one thing that I wanted to tell you before we say goodbye for today. I go back to the web page of our course. Would you please be so kind to read with the independent study, sea wave monitoring? It's very descriptive. I think it is a nice read, and of course it is subjective what I'm saying. And it tells you how waves are monitored. Maybe that something was already discussed by Professor Archetti. And just have a look at this. This may be a descriptive question that I may ask at the exam. And it's not long. I just would like you to study this as an independent activity and autonomous activity. Okay, now let me share the screen. Again, I hope you didn't experience too many connection problems, connection on my side. I will have the same connection next Friday, so you have to be patient. Let me just stop recording and let me ask you if you have any question.